And this is from televiewer image log study. And we can see from here, they interpret the result and summarize. There are three major size of fractures. The first one shown by this red one is the one parallel to the foliation. And there's a green one that is vertical. I think there's some thing wrong with the projector shown, but this one is called by the exclamation. And also there's the blue one. It's some parallel to the horizontal plane, and they interpret it as some historical hydraulic fracture. So I know this can be subjective. It's subject to human explanation and interpretation of that. But I think what we can take away from here is indeed pretty damaged area, and there are fracture site, and not just one fracture site. There are multiple fracture sites in this area. And so all these fractures tend to introduce anisotropy to the rock. And anisotropy, especially in terms of seismic anisotropy, it's elastic property of rock. And they say that the seismic wave speed and the particle polarization will be direction dependent. So if you have a piece of cake like that, and it's isotropic. So imagine we can inject the seismic source from a arbitrary point inside of that. No matter which direction it travels, it will travel at a constant velocity. However, if you have a piece of cake looks like that, and you see all this layering, it can be the parallel fracture size, or it could be the fine layering of sediment like shale. And it's intuitively that the seismic velocity will be different when they travel towards different directions. And still, if we have the source injected in the center and towards different directions, you can see the contour lines. It's not necessarily contour lines, but the lines showing which direction it travels, it will be different. And not only the fractures can introduce seismic anisotropy. We have also this intact rock measurement from the lab. And this is from a previous postdoc with Doug, and he put this transducers on different sides of the samples from New Zealand up and down. And then he measured the change of the velocity or the elastic constants. Also, he keep increasing the confining pressure. So the right vertical line here, it indicates roughly we should look here because that's the target depth. So we are measuring the borehole, which I will talk about later, should have confining pressure close to that kind of interval. And there's also some EBSD measurement from other studies when they cut the samples in different planes and measure how many points of meta are aligned within that plane. And they find when the angle becomes larger and larger in the foliation, there will be less and less points of meta oriented that way. So in that case, it's another evidence that there's preferred oriented crystal as well that contributed to the overall anisotropy. So at this point, we can say there are two types of force or two contributors to the anisotropy we can observe. And one is from the crystal, one is from the preferred oriented fractures. And this is my goal of the idea of what I wanted to do. So I want to define some forward modeling experiment and do it a couple of times until I can find the optimized elastic parameters that space with the data I collect in the field. So this is first introduced about how the wave field is modeled. So this is the most common use scenario that is a vertical transverse anisotropy. It takes 5 parameters, and they are called Thompson's parameters to characterize the anisotropy. And you can see if everything is the same within the horizontal plane, it's called vertical transverse anisotropy, same as VTI. And also, when the geometry can get rotated with 2 more rotational angle, it will become tilted transverse anisotropy media as a TTI. But this is simplified in math because it throws out some higher order terms. And there's maybe I shouldn't say better way, but it's a more general and complete way to characterize seismic anisotropy is to use the whole seismic matrix. Even it's a symmetric matrix itself, so it still takes up to 21 independent elastic parameters. As you can see, if we describe the anisotropy with that, the behavior of seismic wave can be really weird and complicated. In this figure right here, so different color, still we can imagine we have a source in the center of this bench board, and we look from the top of it, and different colors marks the different velocity when it travels towards. And this one has the advantage that if we use the whole seismic matrix, we can combine the rock matrix itself and the influence from the fractal side, which I will show you in some slides later. So the method I use to perform the forward modeling is to use finite difference. So it's to solve the elastic wave equation by matching the propagation area with some very small unit grids, and we keep doing the computing and updating the corresponding value at each point, following the time axis. And the most commonly used is for elastic modeling. It's the velocity stress relation from 1986. And it's also called rotated stagger rate, this one on the left. But there's some issue when we doing the forward modeling with that kind of scheme. And let's show you as an example. So when we are calculate the normal strain, we'll take the adjacent velocity point associated a specific point. In that case, it's this one in the center. And if we are just talk about the second order, second space order, we'll take the 6 adjacent point to one from the top, one from bottom, one left, one right, one front, one back. So we calculate the derivative with the velocity of this 6 point, and that will yield to a normal strain point associated in the center of this cube. It's where the elastic constant is located as well. But when we use this to calculate the shear strain, we'll also use the 6 adjacent velocity, and we'll borrow one from the unit cell next to it, and also from top. And then in that case, if the shear strain is calculated, it's located in this point. So you see there's a half space interpolation between where we have our elastic constant and the point where the shear strain is located. So that half space interpolation area will cause some instability issue, and I will show it later on. And another way is to use this rotated stagger rate. So in this case, the derivative is calculated in a new coordinate that is rotated. So we'll take, let me see, I'll try this. One point from here and another point from here. So each derivative is calculated in this diagonal direction. And then we can use a combination of these 4 derivatives and go back to the normal XYZ. That yields, no matter it is the shear strain or normal strain, they're all located at the center of this unit cell where there is the elastic constant. So by having a scheme like that, we avoid that kind of interpolation error. And let me show you how it looks like. So this is my computing domain. It's a 1 kilometer cube, and I will inject the source in the center of this cube. So on the left, the two are calculated using the standard staggered grid, and the two on the right is from the rotating staggered grid. And the blue frames correspond to that vertical plane, and the two red frames correspond to this horizontal plane. And this one showed you a snapshot of the wave field. So as you see, for Anisotropy case, all these two are the same, and we can still use standard staggered grid to do that kind of computing. But for vertical transverse Anisotropy, yeah, they are still the same. All these are stable and nothing particularly happened. But if the two more rotation angle is applied, you can see that the tilted transverse Anisotropy has some instability when it's calculated by standard staggered grid or SSG. But we can still see it's clear and nice calculated from RSG. And if you recall, as said, we can incorporate the influence of fractal sign into the last displacement matrix by using theory of Stromberg and Sayers from 1985. And each fractal sign can have its own arbitrary geometry and has its own elastic constant. In this one, it's a complex marked by Cn and Cp. So if I add additional fractal sign, it's arbitrary oriented. We can still do this modeling with RSG without any problem. And lastly, partly it's just for fun, or it doesn't maybe not make sense geologically, but we can model the seismic propagation inside the pure crystal in the alpha cores. So you see the SSG has really some severe instability issue when we calculate that, but we can still have a nice and stable result using rotated staggered grid. However, this rotated staggered grid is not always performed better than SSG. I'll show you here. If we have a spacing interval of 2.5 meters, they can give the same kind of result. However, if I lower our resolution and make it to 5 meters, and if you take a closed loop, there are some circles inside circles for this one, and that is called a numerical dispersion caused by you don't have a fine enough spatial sampling, and that happens to the rotated staggered grid. But for the standard staggered grid, as you see, it supplies this kind of numerical dispersion pretty well. So that in other words, we can say it has a better computer efficiency for the standard staggered grid because it supplies this kind of numerical dispersion. So to conclude on this part, I'll say standard staggered grid, it outperforms rotated staggered grid in terms of numerical dispersion and in terms of computer efficiency, because we can achieve the same kind of ordinary result, but we use less endpoints. So that means less memories in terms of industry usage. However, if we want to do the modeling in very complex anisotropy media, the rotated staggered grid is the only choice we have, not not standard staggered grid. So next, I will introduce a little bit about the data set. So it's a borehole from this project called Deep Fault Grading Project in the South Island of New Zealand. And it's the trajectory of this borehole is kind of deviated. And as you see, it's not a vertical borehole. The green part is measured by the three-component geophysics. And the blue lines, it tends all the way down. It's measured by the DAX or distributed acoustic sensing. We have observed both E and S wave because there's seismic scattering happens at the interface between the sediments and the bedrock due to their large contrast in terms of acoustic impedance or the density and the velocity. So this is a photo of the viral size track. This is photo of the withdrawal for orienting. And here it's a example image of the gas data, and this is the synthetic data calculated using the rotating static rate. This is for the near offset one. And for the far offset one, this is from the gas measurement. This is from the forward modeling measurement. So this is the immersion workflow I proposed. So I want to test the elastic parameters, and I wanted to approach to the real elastic parameter of the log as close as much. And on the left-hand side, these are all the steps happening in the numerical world. So I would do forward modeling on the log with some trial elastic parameters, and to obtain some synthetic seismic data, and then to extract some useful metrics from this synthetic seismic data. And in that case, that would be P and S transit time. So to do that, I have also tried some traditional way, like short-term averaging or long-term averaging, but that all doesn't work very well. So I asked some help from machine learning and developed this convolutional neural network. It's also called it's a UNet, as Nat has said. It's a four-layer architecture. So on the left-hand side, it takes in three components of synthetic seismic graph, kind of like a picture with three colors, RGB. And on the right-hand side, it will provide me the predicted P wave and the predicted S wave transit time. So simple as that. I hope I have more time to talk on this. But here it completes all my workflow. Everything on the right-hand side happens in the real world. So at last, I just need to compare this PNS transit time with real or observed PNS transit time. And then I use Bayesian optimization to find the optimized elastic parameters and repeat the whole process several hundred of times. And to do that, one last thing I need is a good geology model. And luckily, we have a colleague who also worked on this data set in this area. Her name is Mary Lay. She used all the red cross points inside this area to produce 3D P-wave velocity tomography. And I use that one to be my geology model. And you can see here is the 3D model of the basement. And this is the trajectory of the borehole. Okay, I really need to speed up. The computing is done using the Purdue cluster called Braun. It has 96 gigabytes of memory. This dimension of the computing domain I have, it has more than a million points to calculate at every second. So this is just give you an intuition how fast or how slow it's compute. So each forward modeling, it has 9 shots. And each shot takes about 90 seconds to calculate. So if I want to run it for 200 iterations, it takes 45 hours, almost 2 days. And here is the result from the lab impact measurement. So this is the result from the inversion. So one thing we can observe is that all these elastic parameters compared to the impact log get lower. And we can, you see the dip, it's 73 degrees. And we can recall the Alpine fault is dipping about 65 degrees southeast. So inversion can retrieve this dipping angle successfully. And in terms of velocity, we can read the number from here and compare it to the inversion result. And we can conclude all these, no matter P wave or S wave, it gets some kind of reduction, about 25%. And in terms of fractional anisotropy, compared with the intact log, you can see the P wave for intact log, it should be more than 10. But in this case, from our inversion of the log mass, it's only 7.9%. But for the shear wave, it's in the level of almost the same, about 10%. So I will conclude here. For the first part about the seismic modeling in anisotropy media, SSD outperformed RSD in terms of computing efficiency, but RSD is the best option if we want to modeling the wave propagation in a very complex anisotropy media. And for the Alpine fault as a very damaged area, we can say the mesoscale fractures cause a reduction of velocity about 25% compared to the intact rock from the lab. And also the P-wave fractional anisotropy is lower than intact rock. And the third one is just a hypothesis that because it has multiple fracture sites, and the fractures is the most tricky role in this area, because if you have a pretty well-oriented fractures, it can actually contribute to anisotropy. But in other case, if it's randomly distributed and there are multiple sets of fractures, it can actually mitigate the overall anisotropy we observe. And that's all I have. Thank you. And